All right, so what we're going to do with this data set right here is we're going to perform a chi-squared test for homogeneity, right? So we're going to check and see if there's a difference in what you do after you graduate from college depending on which department you graduate from. So let me just read the problem. It says a survey of students from the agricultural, arts and sciences, engineering, and IRL departments show the number of students who were employed, went to grad school, or did something else after graduation. The university claims that no matter what department a student graduates from, they do the same things after graduation. Is that true? Okay, so what we're going to look at here, and the important thing for you to notice when you look at these numbers right here, is initially there's going to be some difference in just the raw numbers because of the number of people who graduated from each different department. For example, if you compare the engineering department to the arts and sciences, you can see that 110 more people graduated from the College of Arts and Sciences than from the College of Engineering. So what we're going to be looking at here is if there is a difference, and what we have to come up with here are the proportions. So the thing that I want you to keep in mind is that what they're trying to say is that the proportion of people who go to grad school, get a job, or do something else after college is the same for everyone, right? So that's a key issue here, is that they're saying that the proportions are the same. So if we were to give a null and alternative hypothesis, what would our null hypothesis be? What's their claim? That everything is equal, and that's what a null hypothesis says. So I'm going to say the percentage of students who are employed, go to grad school, yes, thank you. Percentages of students who are employed, go to grad school, or do something else. I'm just going to put or other. After college are the same for each major, or you could call them departments or something, right? So then the alternative hypothesis would just be that they are different. Yeah. So if you want to write the alternative hypothesis is just going to be that they're different. Okay. So with the chi-squared test, there's not really a good way for us to decide if it's more or if it's smaller from the hypotheses. Okay. And we're going to talk about how you can give more information like as we continue with. But from the hypotheses, there's not a really easy way for you to say that it's more or less, right? So what we're going to say is that the null hypothesis is that they're all the same. The alternative hypothesis is going to be that they are different, okay? And I told you I'm going to use several charts in order to pull this one off. Here's the important thing. Remember that the claim is that all students, no matter the department, do the same thing, okay? They do the same things after graduation. So what we want to do is we actually want to come up with percentages. And remember, they said that they do the same thing regardless of department. Okay? So it's no matter what department that they're in. So when I'm doing these percentages, I'm not paying attention to the different departments, right? Because the claim is that all of those should be the same. So what I want to do is I want to come up with a percentage, a total percentage of students who are employed, a total who are in grad school, and a total who do other. And then that percentage should be the same as what they're saying for each one of these. Does that make sense? So what I'm trying to calculate is what percent of these 1,456 students went to or got a job right after graduation. Well, that was 685 out of the 1,456. What is it? 0.47. Okay, so 40% or 47% of all of the students went and got a job. All right, so now grad school, there were 466 in graduate school out of the 1,456. 0.32. And then other, so people who, that volunteer work, going to the Peace Corps, do an internship where you're unpaid, something else like that could happen after you graduate. So that would be 305. You could do a lot of different things. So 1456. And what do you get for that one? 0.21. Okay, so the key here is to kind of keep your mind focused on the idea that we're saying that all of the departments have the same percentages. So we just calculate a total percentage. Don't worry about calculating one for each individual department. So if 47% of all of the students are 0.47 as a proportion, right? I have percents on the screen and I wrote proportions, so please forgive me. If that is the case, if 47% of all students get a job after they graduate, then how many students? Remember, and we got to talk about proportion, because there's a different number of students in each department, right, coming out of different schools. And so, if 47% of all of the students go to be, go to get a job after they graduate, how many would you expect from the agriculture department? Well, there's 448 of them overall, so times 0.47 gives you what? Give me a decimal. 210.56. Decimals are okay in this case, all right? They're okay. Okay? How many from the College of Arts and Sciences? So it'd be the 0.47 times all of the people in the College of Arts and Sciences, right? So how many is that? 227.48. From the College of Engineering? 78.54. And then from ILR? Run this one again, Christian. 70.5. Yeah, this one right here seems like 374 times 0.47. 83.19. Yeah, it should be bigger than that. Yeah, 175. Okay, that makes sense. 175 point 374 times 0.47. We're doing the College of Engineering employed, right? So if we did that, so what did you guys get there? 175.78. Okay, good. If we add all those together, what should we get as the total? We should get the 685, but what we've done is we've redid the 685 to make it an even percentage all the way across the board. Does that make sense? So what we're doing right now is we're calculating, hey, if those percentages are going to be even for each group, what would that look like across the board, okay? So now we'll do it for graduate school. So we have the percentage of people in graduate school is 32%, so 0.32, and some people help with these numbers. Don't let Christian do them all. So be ready to give me those numbers as we go. All right, the next one, the 0.32 times the 484. 0.8. Just even? Yeah. Okay. All right, the percentages for other was 21%, so 0.21. So let's get this bottom row. Say that again. Impossible. 10 what? Now go, Patrick. Next one. Pay attention. So these right here are the expected values if all of the proportions were equal, right? So if the numbers were equally distributed proportionally throughout each department, this is the expected value. So now that we have this, we can calculate a chi-square statistic. And remember, what we're doing is we're doing the expected or the observed value minus the expected value for each individual cell. Okay? Is everybody okay with that? So these are for each individual cell. So this 210 is going to go with this 209. The 227 is going to go with the 198, right? So we're just going to split them up and do them that way. I'm going to make lists, but I got to make sure I put them in a list in a way that's really well organized so that each cell matches up. Okay? So I'm going to go to Stat, Edit, and I'm going to make these lists. I'll go ahead and clear L3 out. I'm going to move over to L1, and I'm going to start with my expected values, and I'm going to work my way through. So 209, 198, 177, 101. Yeah, and I'm just going to go across, and then I'm going to drop down to... Say what? Observe minus expected. So I'm going to, sorry, did I say I was going to start with the expected? I'm starting with the observed values, yeah, and we'll do observed minus expected. Okay, so then the next one, I'm going to drop down and do 104, 171, 135, 39, and 16. All right, so let me go over and do these expected values now. And now I'm starting with this chart, and I got to make sure I go in the same order. So I started top left, went across, and then went down and across. So I'm going to do the same thing. We got 210.56, 227.48. 7. Okay, good. So I've got everything in. So now I'm going to go over to L3, and I'm going to put in my formula again. Right, so it's the observed value. I'm going to open my parentheses. I'm going to do my observed value minus my expected value all squared divided by, let me get this squared right, delete to the second power divided by L2. Enter. Okay, so they've got all of those numbers there for me. So I'm going to exit out of here, and then I'm going to try to get a sum, right? So I want second list, and I want the different types of math I can do with a list, and I want to sum this list up, and there all of the numbers that I want to sum are in L3. So I'm going to use second 3 to give me the third list. Hit enter, and my chi-square statistic is 93.581. Is that what you got? Okay. Now we got to get a p-value now, and I need to stop and talk about the degrees of freedom. Okay. So yeah, you want to check your list? Something up with the list? 2. Not really a way to make it bigger. Yeah, you just got to be really careful plugging them in. Did anybody else get something different than me? Ben got the same thing? You got the same thing? Okay. Okay. What did I say I got again? Go back to my calculator. But I got 93, didn't I? I don't know why I wrote 98 down. Okay. 93. I switched my numbers up, but that was bad off. 93.58. Okay, and in the textbook, they calculated this one at 93.66. So it's just a matter of rounding as to where we are there. Okay. That's a little off. Yeah, but L3 is L1 minus L2 squared divided by L2. So redo that formula. Now, let me wait just a minute and make sure everybody's got the chi-square statistic, because the degrees of freedom here are a little bit tricky. Okay? 685, 466, 305. I feel like I missed those. 305. Okay, so let's talk about these for just a moment. Okay, if I were to ask you how many cells are in here, and let's say it was bigger than this one, it wasn't this small where you could just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How would you tell me how many were in there? What would you do? You'd multiply what? The rows times the columns, and there are 4 columns and 3 rows, right, that make up this cell. So for the degrees of, so there's a total of how many? 12. So how many degrees of freedom do you think there are? Wrong. It's not 11. Okay? And here's why. Remember when it comes to degrees of freedom, I told you that the last thing, like, is locked in. The last one is always locked in. But if I'm talking about this row right here, okay, and I give you the first 3 numbers, and the total is set, when I give you the first 3 numbers right here, does that last number have any freedom? No. So whenever you look at this first row right here, and this really has to do with the degrees of freedom for the columns, right? Because this column can be whatever it wants, this one can be whatever it wants, this one can be whatever it wants, but this one is not. This one's locked in. It's got to be whatever number is going to get me to a total of 685, right? So the number of degrees of freedom in my columns are the number of columns minus 1. Now the same thing can happen with my rows. Let's just say that we're looking at this first column right here. Well, this row can be whatever it wants. This row can be whatever it wants. But what's true about this last row right here? It has to be whatever number is going to let me get a total of 448. So for my rows, how many degrees of freedom are there? There's only 2. It's my number of rows minus 1. So whenever it comes to degrees of freedom for a table like this, it's the columns minus 1 times the rows minus 1. So we're doing the rows times columns, but each column loses a degree of, you lose 1 for a degree of freedom on the columns, and you lose 1 for a degree of freedom on the rows. So we've got 4 columns and 3 rows. It's any time that there's a table like this. The table that we had before was just one list of data, right? That we had earlier when we were doing the goodness of fit test. It was just like one list. So it's just there. it would be one time. I mean, you're doing the same thing there, except it's you don't have multiple rows. Okay, so it makes it easier for you. So yeah, so it's 3 minus 1 is 2 times 3 actually gives us 6 degrees of freedom. Okay, so let's go back to the calculator now and actually get a p-value. Okay, so I'm going to go on second mode. My chi-square statistic is still there, so I'm going to go second distribution. I'm going to get down to my chi-squared CDF, and I want to go from the answer that I just got to 1,000, and I have 6 degrees of freedom. It could be smaller. Yeah, it could be, but not much, right? That is a really, really small p-value. So what do we? So what's our conclusion? We reject the null hypothesis, and we tell the university that what you do after college is affected by the major that you have. That's exactly right. So there is strong statistical evidence that what you do is affected. Is it caused by your major? No, we can't. We don't get causation. We just get correlation, right? So it is different for the different majors. We don't know that it's necessarily the cause is the different major, but we just know that there is a difference. Okay? So our conclusion is to reject the null hypothesis. There is strong statistical evidence because we got such a small p-value. Okay, so strong statistical evidence that what you do after college changes from major to major, or that they're not the same. Okay. Now here's the question, and this is where a chi-squared hypothesis test kind of leaves you wanting, right? Because what we just said about rejecting the null hypothesis was that the null hypothesis is wrong, and these two things are different. Great. How are they different? What's really different about them? What matters here? Okay? So if we want to answer the question of what really matters, okay, and why these two things are different, or which department has fewer people getting employed, which department has more people that are going to grad school, which department has fewer people who are doing something else after college. If we wanted to figure those things out, there is a way. Okay? So what we're going to do is we're going to come up with a standardized residual. Okay? A standardized residual for each of these. So that we can figure out, which departments are high and which ones are low and in what categories. So our standardized residual is what we're going to look for now. And I want you to think about the empirical rule, okay, 68, 95, 99.7 rule. Whenever we start coming up with these different residuals. So I've got each department listed here. I'm going to go back and I'm going to calculate these residuals using my calculator because I've already got the observed and expected values plugged into my lists. Okay, so I'm going to go back and calculate each of these using that. So now in L3, I'm just going to go into my list, stat, edit. And for L3, I'm going to change it because L1 and L2 are my observed and expected values respectively. So I'm going to clear this list out. Clear, enter. And what I want to do now is I want to use this formula. I want my observed values, that's L1, minus my expected values, that's L2, divided by the square root of my expected values, that's L2. I'm just using this formula and then enter. And now I'm just going to try to plug these things in. I know that I went this way, right? So this first residual goes right here, negative 0.1075. The next one is negative 1.955, 0.09202, 3.6325, negative 3.207, 1.3021, 3.5028, negative 2.165, 4.4, or sorry, 4.2, 4.218, 1.325, negative 4.462. Now let me get to my last one. Negative 2.762. So these are standardized residuals. In other words, these are standard deviations. So which of these, if you're thinking about them like standard deviations, looks really strange to you? The 4 and the negative 4. You could maybe even say something about the ones that are larger than 3. But if this is a positive 4, what does it mean about the number of ag students who are doing other after college? It's really high, right? There's a high number of ag students doing something else after college, and the number of engineering students doing something else after college is extremely low. So the standard deviations help us to see what's really happening after we get done with our test for homogeneity.